In 1999, Carlyle Johnson patented a unique mechanical one-way bidirectional clutch. The new product line was released in 2000 and involved a series of balls and ramps placed in configuration to bias the friction disc in one direction and prevent motion of torque transfer from one side. The easiest way to describe the operation of this device is to see it perform. Looking at the sample model on the table, the sample model is comprised of four major components: the input shaft with handle for rotation, the Carlyle Johnson MTL with observation windows that will allow us to see the internal components in operation, a Carlyle Johnson spring-applied mechanical clutch that is used to couple and uncouple the two halves of the output shaft. This is accomplished by moving the handle and releasing the spring force that is used to lock the friction disc. Similarly, if the handle is released, the clutch is engaged by the internal springs and the output shaft is coupled. And finally, a load or torque placed on the output shaft by the weight that is hanging at a 2-inch radial distance from the center of the shaft. For example, if the weight is 5 pounds, the applied torque is 10 inch-pounds. If we focus on the MTL, we can observe in the current mode of operation the weight hanging from the output shaft of the model placing a torque on the output shaft in the counterclockwise direction. The weight is not moving and is held stationary by the MTL. The input shaft and handle are stationary. The spring-applied clutch is coupling the two halves of the output shaft. The output shaft is behaving as though it were one solid piece. The torque will not backdrive from the output shaft to the input shaft. If we move the handle in either direction, clockwise or counterclockwise, by placing a torque that is slightly greater than that of the torque placed on the output shaft by the hanging weight, we can move the input shaft and output shaft in either direction. Notice the input and output shaft rotate in unison. Whenever and at whatever position I decide to stop rotating, the input shaft, both input and output shafts, lock and backdriving is not possible. The handle does not rotate. The same is true if we move the weight to the opposite side and create a clockwise torque load on the output shaft. In summary, the MTL allows torque to pass in either direction when the torque applied to the input shaft is slightly greater than the torque applied to the output shaft. The simplest applications for this device is in elevators, escalators, cover closure devices, winches, valves, etc. By combining the MTL with a spring-applied clutch, we can achieve several modes of operation that are useful. The clutch will act as 1. A brake, or 2. A torque limiter. Braking mode. As the model sits in its current state, the clutch is coupling the two halves of the output shaft. When we release the clutch, the weight will drop. This is due to the decoupling of the output shaft. Notice the input shaft does not rotate. When we slowly let the clutch re-engage, the two halves of the output shaft are coupled and the clutch acts as a brake. This occurs because one half of the output shaft is locked by the MTL. The MTL will not allow the output shaft to rotate or backdrive into the input shaft in either direction. In other words, half of the output shaft is locked by the MTL and the other half is free to rotate only when the clutch is disengaged. So at this point, the clutch is acting as a brake and stopping the torque load placed on the output shaft by the weight. Once the clutch is fully engaged, it will act as though the output shaft is one piece. Again, notice that the input handle did not rotate in either direction during this operation mode. But if I rotate the handle by placing a torque on the input shaft greater than that of the output shaft will rotate in either direction until the torque applied to the input is less than that applied to the output. Torque limiting mode. In the stationary mode, the clutch will act as a torque limiter. When the torque load placed on the output shaft is greater than that of the torque capability of the clutch will slip and the output shaft will rotate, but the input shaft will remain stationary. Notice the handle does not move when I pull on the weight in either the counterclockwise or clockwise direction and exceed the static torque rating of the clutch. In summary, by adding a spring-applied clutch with an MTL, we can add additional features of soft braking and torque limiting to the system. This type of device is used when two modes of driving the input are required, such as manual backup to a primary motor drive. If the manual clutch were replaced with an electrically released spring-applied clutch, and we added a motor to the output of the clutch, then we could turn on the motor and simultaneously energize the clutch, thus decoupling the output shaft. The motor can now rotate the output shaft freely in either direction. When we turn off the electricity, we would couple the two halves of the output shaft, and the clutch will act as a dynamic brake to stop the output shaft and associated load. The manual handle can then be used to drive the input shaft through the MTL. Once the shaft is in the proper location, then the handle can be released and the output shaft is locked in position. Adding a backup manual mode of operation is essential in some applications. Typical applications for an integrated clutch and MTL include azimuth and elevation drives, escalators, door closures, etc.